Welcome to the Explainer. Today we are diving headfirst into an incredible new development that literally solves one of the biggest paradoxes in AI right now. Think about it. How do you collaborate on these massive, highly sophisticated models without exposing the highly private, strictly regulated data that actually powers them? It's a huge challenge.
Well, we're breaking down a totally game-changing framework from Karaboga and Karaarslan over at Mugla Sitki Kocman University. Honestly, if you're working anywhere near the intersection of AI, data privacy, or cloud security, this is absolutely crucial for your day-to-day operations. Here's the deal. AI gets smarter the more diverse data it eats, right? But the world's most valuable data, stuff like healthcare diagnostics, people's financial histories, proprietary corporate analytics, it is all locked away in heavily guarded silos. So we're stuck in this paradox. We desperately need that data to build better models, but we absolutely cannot share it because of privacy laws and, frankly, massive competitive risk.
Enter Cross-Cloud Federated Learning, or CCFL for short. This is the practice of collaboratively training AI models across multiple independent cloud providers. But here is the kicker. You do it without ever exchanging the raw data. It's such an elegant fix to the privacy problem. Instead of dragging all that sensitive info to a vulnerable central server, the AI model itself actually travels to the data. It learns locally and then just sends back the mathematical updates. But there's always a catch, right? Relying on a bunch of different cloud environments, different companies, different cloud providers, totally different security standards, that introduces a massive new vulnerability problem. Just imagine a setup with distinct institutions, say a hospital, a major bank, and a huge e-commerce platform. They're each operating in their own independent, highly secure cloud. Now they want to team up to train one global AI model, maybe for fraud detection or pattern recognition, and it's all coordinated by a central federator. The hospital's patient records? Locked down. The bank's ledgers? Locked down. Only the math, the actual gradient weights the AI learned, gets sent out. But because you've got these completely different domains pooling into one global learning process, the attack surface just explodes. And since that central federator literally cannot see the underlying raw data, trusting those incoming math updates turns into a seriously high-stakes digital battle. Our sources highlight 3 major adversaries trying to exploit this zero-visibility setup. First up, we've got Sybil attacks. Second is model poisoning. That's where bad actors actively try to wreck the global model or sneak in hidden backdoors. And third, inference attacks, where some highly skilled attackers try to reverse engineer and reconstruct your sensitive data just by looking at the mathematical shape of the updates. Wild, right? Let's zoom in on that first threat, the Sybil attack, because the mechanics here are just insidious in a federated system. You can think of it kind of like a malicious, highly coordinated voting block. An attacker sneaks multiple fake identities, Sybil nodes, into the network. And because these fakes all submit very similar, intentionally manipulated updates, they start to heavily bias the whole AI model. They're basically using sheer numbers to drown out the honest updates from our legitimate hospital or bank. In a cross-cloud setup where you don't inherently trust every single connection, a good Sybil attack can silently destroy the mathematical integrity of the entire global model. So, what do we do? How on earth do we fight back when we can't even look at the raw data? Well, Karaboga and Karaarslan developed what they call a 6-layer defense shield, designed to protect every single stage of the data's journey. And it's brilliant because it's so logical. It applies cryptographic privacy right at the source. It actively filters out bad actors while the data is in transit. It securely combines everything, and then it wraps it all up with an immutable audit log for total transparency. Let's break those layers down. This whole thing operates in a specific sequence, right from the cloud side down to the server side. Layer 1 kicks things off with local differential privacy. This adds just the right amount of statistical noise to mask the data, stopping those inference attacks cold without ruining the actual learning value. Then Layer 2 brings in zero-knowledge proofs, basically letting a client mathematically prove their work is legit without revealing any private info. Okay, so as the updates hit the server, Layers 3 and 4 step in as the bouncers. They use similarity clustering to group up and catch those coordinated Sybil attacks, and z-score filtering to mathematically identify and drop outliers trying to poison the model. Layer 5 guarantees secure aggregation so the server can compile everything blindly. And finally, Layer 6, blockchain logging. This locks the entire interaction into a distributed ledger, giving you a completely tamper-proof audit trail for the round.
Now look, a theoretical framework packed with heavy cryptography sounds amazing on paper. But you know as well as I do, the true test of any security architecture is how it survives on the actual digital battlefield. So the researchers put this 6-layer architecture through the ringer. They ran rigorous simulated threat modeling to find out exactly when and how it would break under intense pressure. And man, this is where that layered defense truly shines.
The contrast they found is just staggering. They set up a brutal scenario, a 50% adversarial attack. That means literally half the network participants are malicious nodes actively trying to tank the model. Under that kind of fire, standard federated learning completely collapses, suffering a massive 60% drop in accuracy. It just learns garbage. But under those exact same conditions, the Secure-CCFL framework barely flinches. It absorbs the blow with only a 12% accuracy drop. It basically keeps near baseline performance. It proves that the clustering and filtering caught the attack and shut it down before it could ruin the global model.
When you look at the granular metrics, you see exactly how it pulled this off. It's actively neutralizing threats with an 88% precision rate for detecting those fake Sybil identities. And that high precision is huge, because it means honest participants aren't getting accidentally kicked out of the training round. We definitely don't want to waste good data. Plus, the system hit a massive 91% recall rate for catching poisoned updates before they could merge. Because the central federator acts as this highly intelligent zero-knowledge bouncer, the math and the blockchain combined give you verifiable, rock-solid cross-cloud trust. Now, of course, nothing in computer science is ever completely free. There's always going to be some computational or bandwidth trade-off for wearing this much armor. Normal federated learning takes about 6 megabytes of communication overhead per client per training round. Slap on differential privacy, zero-knowledge proofs, and the rest of the stack, and that bumps up to 9.4 megabytes. But hey, as the researchers point out, we're talking about modern cloud infrastructure here. An extra 3.4 megabytes, that's literally a fraction of a second on a fiber connection. It is a tiny, totally acceptable price to pay for guaranteed data confidentiality and structural integrity in a completely untrusted environment. Seriously, if you're building the future of collaborative AI, security cannot be an afterthought anymore. It's got to be baked deep into every single layer from day one. You can read Karaboga and Karaarslan's full study in IEEE Computer. Definitely cite them in your next project. But I want to leave you with this thought. As these cross-cloud frameworks get stronger and trust becomes mathematically guaranteed, are we finally going to see fiercely competitive industries like rival hospital networks or giant global banks actually pooling their collective knowledge to build global AI supermodels? It's a wild possibility. Thanks so much for joining me for this explainer, and I'll catch you next time.